pretty straightforward. It's a bathtub water height over time. If you're running water in, it would be sort of a linear upward type of function, and then quickly someone getting in, I guess, would raise the water level to a certain fixed point. The person is in the bathtub. Perhaps they reach partway out because it doesn't drop to that original level before they got in. They reach out for the soap, shampoo, whatever. Then they finish up in the tub and they get out and then they drain the water. In real life, I think it would actually drain in a concave curve like that, but that's a detail. This is just determine whether the function is even or odd or neither. There are even exponents. That's where the even function comes from. So when I plug in a negative x right here and then I simplify it based on our rules of exponents, I get the same thing with positive x. That is the very mathematical definition of an even function. Here we've got 4 basic functions. There's no matching, but you would have been given an actual matching thing on a test. 3x, that's just a linear function. That's just going straight through there. And that is that one for A. 3 to the x is exponential. Do that in green. That's hugging this line. It goes through the point 0, 1, goes up. Then 3 to the x, that's going to be our cubic function. It's going to go negative when x is negative, positive when x is positive. It's got that familiar cubic function curve to it. And then the cube root is the one that maybe would trip some of you up, just because remember it's an inverse that is allowed to go negative. You can take the negative cube root. Some basic family of function type stuff. For the next one, a parent function that is a square root is going to go like this with its initial point at the origin. There is no defined square root of a negative, so it just starts at the origin. Then what it's been done is it's been shifted a units to the left, because we want to know when is this equal to 0, and it's equal to 0 when x is equal to negative a, and then it's going down b. So that's all you need to do, is just sketch the shape of that. What is the domain? The domain is going to be all of our x values can be equal to but must be greater than a. All right, x has to be greater than or equal to a. The range, the output, for this function then, it would be greater than, that would be that it has to be greater than or equal to negative a, x values are greater than or equal to negative a. The range values coming out are when this is 0, it's going to be equal to negative b. So we'd say f of x is greater than or equal to negative b. All right, find the inverse. All right, so we start with the original function. We swap out the f of x. We write y equals minus b plus square root of x plus a. Then we swap the x and the y equals minus b plus the square root of y plus a. Then we just solve for y, get y down there by itself. So I'm going to have it be x plus b when I add b to both sides. Then I'm going to square that, and that will be equal to y plus a. So when I subtract a from both sides, I will get that inverse function as x plus b squared minus a, okay? And the domain and range are simply going to be these guys reversed if I have done that correctly. So I'm just going to shorten up this key by doing that. You just swap them, right? That should make sense. An airplane is flying at a speed of 350 miles per hour at an altitude of 1 mile. Here's our airplane. Very fast airplane, very badly drawn. And it's flying at 1 mile above some radar installation or something like that. And so we could say that that's the radar installation. That's what that's looking like when it's directly above. It makes a right angle. We just want to know what is an expression for this distance that it's traveled going this way. Well, the distance something traveled is just velocity times time. If you want to write it as a function, I guess this is kind of a nice way to do it. And I just got a low battery warning there, but I think I'm good till the end. D of t is just simply the velocity times time. Well, this is the straight line distance s that we're trying to find, and that's going to be based on Pythagoras. So if that's 1, s then is equal to the square root of this distance 1 squared plus that distance, which is vt in parentheses squared. And that also could be thought of as a function of s. So that is like a composite function. We're subbing in this first one into where it would be just like a distance. All right, so then this is just using laws of exponents. This then would be x to the 2n plus, and then 3n minus 1 all over x to the n plus 2. Well, that's going to be the same thing as x to the 5n minus 1, and then subtracting the lower exponent n plus 2. Well, 5n. So 5n minus n is going to be 4n, and minus 1 minus 2 more is minus 3. So that would be the simplest way you could write that based on the laws of exponents. Speaking of laws, this is laws of logarithms. To write a single log, well, we're going to do this inside first, and when you're adding two logs with the same base, they're both natural logarithmic base, it's going to be ln. When you FOIL those out, you're going to get a squared minus b squared, right? That's like the difference of two squares. And then when you subtract a log, that's like dividing. That 2 comes in as an exponent, c squared. So that's the single log with this 1/2 out in front. Well, that comes in as an exponent. So this just then is going to be the ln of a squared minus b squared all over c squared. This whole thing square rooted, and leave it like that. And do not, repeat, do not think that that is going to be equal to, it is not equal to a minus b over c. It does not work that way. All right, see me after class if you have a question on that one. Compare the functions x to the 5th and 5 to the x by graphing both in several viewing rectangles and sketching the best possible graph. Find all points of intersection. Well, this is where having some math smarts maybe helps, in that you can recognize pretty quickly that 5 to the 5th, when I plug in 5, is going to give me 5 to the 5th. So these are going to be in agreement at the point 5 comma. Well, what is 5 to the 5th? 5 to the 3rd is 125. 5 to the 4th is 625. So it's going to be a big number. We can just leave it as 5 to the 5th. You can multiply it all out, but that is going to be, 1, 2, 3, 4, 5, and way the heck up there. 5 to the 5th. But what's happening in that it's an odd function, so whatever this is doing going up is going to be going like that, going down. It's going to go through the origin. When it's negative, it will be negative. Meanwhile, the exponential function is going along like this, and it's going to hit down there at 1. It's going to look ridiculously close. I'm exaggerating that, but then it's going to go up. I'll put that mark down like that, and it'll go up like this, and then it'll actually grow more steeply like that. And then there will be another point of intersection when this gets way up high. I'm going to have to, I'll put that on the answer key in the scan I'll put up. All right, so you'll see that there, because I want to get this done within my about 10 minutes, so I'm not sure I'm going to make it. This one is an interesting one. Is it even, odd, or neither? Again, by inspection, you can pretty much look at this and see that when I plug in f of minus x, right, that I'm going to get something that will be the same as when I plug in minus f of x. Does that make sense? That when I plug in the negative, it will be negative, but it'll be the same thing as if I just change the sign of the value when I plug in the positive. So that's the definition of an odd function. If I graph this carefully, I think having put this in a prior lifetime on this calculator here, this is a graph after playing around with the window a little bit. You can see that when I plug in 0, it's going to be 0. But you're going to get very small values. So my y values are 1/10, plus and minus 1/10 about in the y values. And then my x's are going out to plus and minus 50 on that. So you just want to get in the habit of plugging in some points that you know are going to work and then looking for those values. For instance, if you plug in 1, you'll get 1 over 101. If you plug in 10, you'll get 10 over 200. So 10 over 200 will be the same as 1 over 20. So you can start to see where you'll get values and what the y value will be that will correspond with that. So that's about 50 and minus 50, and this is about 1/10 and about minus 1/10. Okay, and again, just trying to get this mostly done in a short amount of time. Here's our parametric equation. So we've got a golf ball that's traveling horizontally at about 80, this is meters, about 80 meters per second. And it's traveling vertically upwards initially at 40 meters per second, but gravity is pulling it down. And we can surmise that if it's going up and down in the y, where it's going constant in the x component, that it's going to be something that goes in a parabolic shape like this. Okay, and we could type that into parametric, and we could trace through it, and we can find out all sorts of good things. We could find where the highest point is, where it comes down to 0. All right. Was it a long drive or a short pitch onto the green? Combine the two equations. I'll do this first. If we have x is equal to 80t, then we know that t is equal to x over 80, dividing both sides by 80. And then I can sub that into the other one, so y is equal to 40 times x over 80 minus 4.8, and then x over 80 squared. This one is begging to be simplified, but you really don't have to do a lot of simplifying. 1/2 x minus 4.8, and I'm just going to keep it in this form. Well, x squared over 6,400. And I suppose I can write it as 1/2 x minus 448 over 64,000 x squared. All right, that's at least relatively simple with integers. Okay. To put this is the world's oldest calculator here. Go to mode, go down to parametric, hit the y equals. If I type in 80 and then hit the variable, I get the t, put in 40 with the t minus 4.8 t squared, and then I go to a window. I'll make it go from t from 0 to maybe about 6 is about right. Golf balls can be in the air a pretty long time. The time step, I'll go 0.2 in the beginning. My minimum x, I'm going to have that be 0. Golf balls can go like 300. I'm making up those equations, so you never know. Y minimum, the ground is at 0, and then it could go maybe, I don't know, 60 meters in the air. We'll see how that works. And here's the graph. Okay, so that is one heck of a golf swing, all right? So that's going to be going a long ways. Maybe this is on the moon. And let's go to 1,000. Let's see how good that. It's still not coming down. That is an amazing golf ball. All right, so goes to show how hard it is to make up problems like that. I'll go higher in the y values as well. I'll go to 200. Okay, well here it's still going up and down after 6 seconds, so I'm going to make this golf ball go, it looks like, to about 12, and that will at least show it. All right, so I won't take too much more time because I got to get this posted, but you can trace and you can arrow, and you can see there's the golf ball going up. When is it at the highest? When it's 336 meters along.